Hello students, our next topic is the principle of equivalence. In the previous topic related to uniformly accelerating system, we have found that there is a fictitious force acting on non-inertial frames, F fictitious equal to minus ma. Related to that, there is an equivalence between non-inertial frames and inertial frames. Here in this topic, we are finding out that the law of physics in a uniformly accelerating system are identical to those of an inertial system, provided that we introduce a fictitious force on each particle, F fictitious equal to minus ma. So, the laws of physics in a uniformly accelerating system are identical to those in an inertial system, provided we introduce the fictitious force ma. We know that a is the acceleration of the system. Okay, so F fictitious is indistinguishable from the force due to a uniform gravitational field G that is equal to minus A. Both gravitational force as well as the fictitious force are constant forces which is proportional to mass. So, in a local gravitational field G, a free particle of mass m experiences a force F equal to mg. Consider the same particle in deep free space. Deep free space means there is no gravitational force acting on the system. So, if it is in a non-inertial system uniformly accelerating at a rate a is equal to minus g, then it also experiences an apparent force F fictitious that is equal to ma that is equal to mg. So, we cannot distinguish the two things, the two type of experiences when a system or a mass, a particle m experiencing a gravitational acceleration g and another system which is non-inertial without any gravitational field which is uniformly accelerating at a rate a is equal to minus g. Both of these cases the free particle experiences a force equivalent to mg itself. Okay. So, in order to distinguish, can we distinguish these two situations, or how can we separately analyze these experiments? This is a thought experiment by Einstein. So, in this first case, a man is holding an apple in an elevator. The elevator is at rest in a gravitational field G. So, there is an acceleration towards downward direction as usual. The elevator is at rest. Okay. Now consider the same man. So he let go of the apple. Okay, he drops the apple and he sees that it falls with a downward acceleration a is equal to g. So this is our observer. When he drops this apple, he sees that the apple is going downward with an acceleration g. Okay. Now consider the same man in the same elevator, but this elevator is in the free space. That is, there is no local gravitational field acting on this elevator. Okay, and this this elevator is accelerating upward with an acceleration a is equal to g. So here the elevator is moving up with an acceleration g. Okay, the man is again he drops the apple and it again appears to him to accelerate downward at the rate g. So according to him, this accelerator is moving upward with an acceleration g. He observes this motion, the motion of the apple, as downward, the same as above, with the same acceleration g. There is no way to distinguish between acceleration of the elevator and the gravitational field. So the observer inside a non-inertial system or non-inertial frame, he cannot identify whether this is the case or this is the case, or we cannot distinguish between the acceleration of the elevator and the gravitational field. So the next case is that when the elevator is freely falling in the gravitational field. Okay, if it is falling freely under the gravitational field, the elevator and all its contents are accelerating downward at the rate g. It is similar to free fall. Okay, if the man releases the apple, what will be his observation? It will be floating as if the elevator were motionless in the free space, because the elevator and its contents along with the apple all having a downward acceleration of g. So he appears to so according to him, it will float in the elevator. So Einstein pointed out that the downward acceleration of the elevator exactly cancels the local gravitational field. So from the point of view of an observer in the elevator, there is no way to determine whether the elevator is in free space or whether it is falling in a gravitational field. So we can define now what is the principle of equivalence. There is no way to distinguish locally between a uniform gravitational acceleration g and an acceleration of the coordinate system a is equal to minus g. So this is the principle of equivalence. There is an equivalence between the two cases. So we cannot distinguish locally between a uniformly accelerating system with g acceleration and an acceleration of the coordinate system that is equal to minus g. So by saying this, there is no way to distinguish locally, we mean that there is no way to distinguish from within a sufficiently confined system. Confined system means the observer was inside the elevator. Okay. So for instance, if you are in an elevator, if you are inside the elevator and observe that the free objects are accelerating downward with an acceleration a. If you are inside an elevator and you see that some objects are moving downward with an acceleration a. So to him, to the person inside the elevator, there are two possible explanations. The one is there is a downward acceleration g and the elevator is at rest or moving uniformly in the field. This is one of the explanation. That is, the elevator is at rest or moving downward uniformly. There is a downward gravitational acceleration g. That is why you can see the objects falling with a rate a. Okay. The second explanation is that there is no gravitational field, but the elevator is actually accelerating up at a rate a is equal to g. These are the two possible explanations, but he cannot distinguish between these two cases. Okay. Thank you.